So we're still talking about the concept of concentration of a solute in a solvent here. And we had looked at a couple of ways of measuring concentration or expressing concentration. But we had settled on the one that is most common, that of molarity. And we had started talking about that as the preferred method of expressing solution concentration. We went over how to make a particular concentration and molarity of a substance, the proper way to do that, and we looked at some general calculational examples, a couple of how you might see them presented to you in problems on a test or a quiz or an exam and so forth. And we looked at a specific quality of molarity than that of ion concentrations. It matters whether we're talking about for instance, the concentration of an ionic solid or an ionic solute in a solvent, or the concentration of one of its ions in that in that particular solvent, because it can be different. It can be different based upon the molar amounts of the various different ions that make up one unit of our ionic structure. So we're going to move on. We're going to look at another way of looking at molarity, sort of a trick, if you will, and that is with respect to solution dilution. See, I'm a poet and don't even know it. Yes, the solution dilution equation is used for diluting very concentrated stock solutions to a lesser desired concentration. Typically, when a chemical company sends you something through the mail, if you get it into a dissolved state, it will send up the most concentrated possible way in order to save money on shipping costs. And then the chemist there opens up that very concentrated solution and dilutes it down to a concentration which they like. So the solution dilution equation is just that. It's an equation. M1V1 equals M2V2, where the M's with the line under it are the initial and final concentrations in molarity, and the V's are the volumes, the initial volume and a final volume. And you'll always know that we're talking about a solution dilution example problem if they have the term dilute or dilution or something like that in there. We would know for instantly we're going to plug this into the solution dilution equation. For example, to what volume should you dilute 0.1 liters of a 15 molar NaOH solution to obtain a 1 molar solution? Well, we have our initial pieces right there. The initial pieces are the initial molarity right there and the initial volume right there. So we can put these all on one side of the equation, and then we look for the other side of the equation. We have to look at what we are solving for. So we want to obtain a 1 molar solution. So that would be M2, the final molarity. So really, we'll plug that in, but we're looking for that final volume. So this becomes elementary at this point. It's essentially 15 times 0.1 divided by 1. And we solve for V2, and we end up with 1.5 liters. Where we find a very high usage of molarity is in what's called solution stoichiometry. Solution stoichiometry, and basically we have a number of liters of a known solution, and we have to calculate the number of liters of an unknown solution. And obviously we have concentrations coming in to play on that. But as we'll see in various examples, when we see in a word problem like this, or in a quantities type of problem that we've looked at before, where we're going to have to do a dimensional analysis, what do we have, what do we want, and how are we going to get there, we're going to find that the molarities themselves are almost always used as a per expression, hiding in plain sight that we are going to extract out of that. If you remember in our quantities chapter when we were looking at chemical reactions, if I have 15 grams of this particular starting material, how many grams of product can we theoretically produce? And we found that we can't go directly mass to mass or grams to grams. We had to take that circuitous route. grams to moles to moles to grams. That three-legged journey. In this case, or in that case, going from grams to moles, we use the molar mass of whatever substance we were talking about, and then the mole to mole comparison was we used the balanced equation that's in the word problem. It's a little bit different here, but similar when we're talking about solution stoichiometry. Here we start with a known amount of liters of one substance that's dissolved in a solvent, and we want to go to the number of liters or an unknown number of liters of dissolved of another one. So rather than grams to moles to grams in this case, it still is a three-legged journey. We convert from the known liters to known moles like we did before, but since we're in solution, we use the molarity that's given, and we'll see how to do that. Moles of the known quantity to moles of the unknown quantity, we do exactly as we did before, using the coefficients from the chemical equation. And moles of our unknown quantity back to liters of our unknown quantity, again, we would use the given molarity. Again, this will be similar to those circuitous routes that we took before in the quantities in chemical reactions, but it is a little bit different. We're using these molarities now. So let's see how this might work. So let's see how this plays out on an actual word problem. This is solution stoichiometry. Consider the following reaction equation. 2Ki plus PbNO32 goes to PbI2 plus 2KNO3. And then the question, we've given the balanced equation. Here's the question. How many liters of a 0.115 molar Ki solution is required to completely react with 0.104 liters of a 0.225 molar PbNO32 solution? Before we get into the meat of this, I'd like to look back at that balanced chemical equation of reaction. Notice the only two players we're associated with up here are the PbNO32 solution and the Ki solution. That's the only thing we're looking at. So all of the product profile can be crossed out. It simplifies what we're doing here. Now, the second thing I'd like to look at is this is going to be a dimensional analysis, and our first question of those three age-old questions in dimensional analysis is, what do we have? Well, we got to seek out a number. Turns out there are three numbers in this equation. So at first we're a little bit flummoxed and we don't know which one we're supposed to use here. Well, let's take a closer look at these numbers. You'll notice that two of these numbers are molarities. That's a molarity. That is a molarity. And as I said before on the previous slide, molarities in these types of questions almost always are per expressions hidden in plain sight. Given that, if those two that I just circled are per expressions, there's only one more number. That has to be the number we're going to start with, and it is, because these other two are molarities. But let's take a closer look at these molarities. Now, we can force this into a numerator-denominator per expression. For instance, the 0.115 molar Ki, what it means is 0.115 moles of Ki per 1 liter of Ki solution. Similarly, 0.225 molar PbNO32 is 0.225 moles of PbNO32 per 1 liter of that solution. So we're going to be using these, obviously, since we've taken the time to realize that they are per expressions. So now we start out. What really is our first numerical component? What do we have? Well, it's that 0.104 liters of PbNO32 solution. What do we want? How many liters of this Ki solution? And we put that over on the other side, right above my head here. And how are we going to get there? Well, if you'll remember, we use that three-legged journey, that circuitous route A three-legged journey means, in this case, in all cases really, 3 per expressions. And those per expressions guide the path of us from grams to liters, from liters to moles to moles to liters. So let's see how we would do that. We are now starting out in liters of lead, this lead nitrate. And there it is right over here, And here is liters over here, and here is moles. We're going to use that as written as the first per expression in that. And that cancels us out of liters of PbNO3 and into moles of PbNO3. Now that we're in the land of moles, all we have to do is look back on the chemical equation of reaction and find that that is a 2 to implied 1 molar ratio. So we're going to set that up so that the moles of PbNO3 cancels using that 2 to 1. So these moles now go away, and we're in moles of Ki. Well, moles of Ki to liters of Ki here over on the left now, that is our per expression we're going to be using, times 1 liter of Ki solution per 0.115 moles of Ki. Notice that I had to take the reciprocal of that in order for moles of Ki to cancel. And finally, that puts us in liters of Ki solution, which is exactly what we're looking for. It is then and only then that we reach for our calculator and put in the final number of liters of Ki solution. So let's look at another way of carrying out solution stoichiometry. And this way is by what's called acid-base titration. This is actually a lab that we're going to be doing very shortly. Acid-base titration essentially means that we have an acidic solution to which we are adding slowly and methodically an NaOH solution to it through a burette, which means we can know exactly the volume of NaOH solution added to it. And we keep doing that until all of the acid is used up. Essentially, we've neutralized the reaction. We've taken base and we've added it to acid, and the reaction is finished. And when that happens, we add an indicator so that the acid solution will flash pink. It means it's neutralized, we've changed color, and then we can measure the volume, if you will, for the starting volume to the final volume of NaOH and calculate the concentration of that original acid solution. This is ready-made for solution stoichiometry. So let's look at an example of this. Really, that's all just superfluous. Really, the important thing here is we're going to be using this reaction of a strong acid and a strong base in a word problem. So let's take a look at that. So let's take a look at a representative problem here. Consider the following reaction equation, exactly as we had on the previous slide. HCl plus NaOH goes to H2O plus NaCl. Question: how many liters of a 0.113 molar NaOH solution is required to completely react with 1.25 liters of a 0.228 molar HCl solution? We're only dealing with the reactant profile. Again, it doesn't have to be, but that is the case here. So our entire product profile we can just say goodbye to, because that helps us simplify the problem, and indeed we're not doing anything with H2O and NaCl, so it makes it a little bit easier. So let's take a look at the numbers we have here, because what do we want, or rather what do we have? We're going to have to put a number down. Well, there's 3 numbers there, just like before. And we see that, and 2 of them are molarities. They are indeed molarities. So this one is a molarity, and that one is a molarity. So we're going to immediately assume that those are per expressions and pull them out. Again, 0.113 molar NaOH means 0.113 moles of NaOH per 1 liter of solution. And 0.228 molar HCl means 0.228 moles HCl per 1 liter of HCl solution. So here now we're able to dissect through and realize that there really is only one number here when we say what do we have, and that is that 1.25 liters of our HCl solution. So I'm going to put that down over on the left. What do we want? Similar to before, how many liters of NaOH solution? That goes way over on the right, again, right above my head. And how are we going to get there? Well, we're going to be using that circuitous route, liters to moles to moles to liters, because we're doing solution stoichiometry. And in this case, we start with liters of our known quantity, and we have to go to moles of our known quantity. Our HCl solution is right here. That's a doorway between liters of HCl solution and moles of HCl. And we're going to use that as such. We're going to multiply through so that we are able to cancel out of liters of HCl solution and end up with moles of HCl, which is great. We end up with moles of HCl. Now we're in the land of moles. I keep saying this. And when we're in the land of moles, we look no further than the coefficients in front of the components of the chemical equation. That is an implied 1, 2, and implied 1. 1 to 1 to get us moles of HCl, our known quantity, into moles of NaOH, our unknown quantity. And again, canceling through as we go helps us to follow along. We've taken 2 steps on our 3-step circuitous route. We're in moles of NaOH. I need to get to liters of NaOH. Now remember, we have another per expression here, that molarity. That's the doorway between moles of NaOH and liters of NaOH solution, just like we said before with the HCl example. In this case, as before, we're going to have to take the reciprocal of this particular per expression right here, turn it on its head, and the only reason for that is now we can cancel numerator to denominator moles of NaOH. And we're left with liters of NaOH solution. That is indeed what we're asking for. Then and only then do we reach for our calculator. And we come up with the number 2.52 liters of NaOH. Final answer. So molarity is usually the go-to method of expressing concentration in almost all cases now. We are going to look at a different method of determining solute concentration, something that looks very similar to molarity, and that is molality. Molality being a different method of determining solute concentration, but it's more specific due to the fact that molarity can fluctuate. It can fluctuate because molarity is based in moles of a solute per 1 liter of solution. Now, volume can fluctuate in a number of different ways with changes in temperature, changes in state, so that if we have the same number of moles in a solution, if that volume changes, well, the molarity changes too. It fluctuates. So let's look at a couple of ways that molarity can fluctuate, or rather the volume of the solution can fluctuate. Solution volume can change with changes in temperature. So for instance, if we had a solution with 2 moles of solute in it, and at 5 degrees Celsius, say we had exactly 1 liter of solution here. If we came back later, I can't really think of a situation where this would happen, but if we did, and it was 95 degrees Celsius, well, that solution would have expanded. Things get hotter, they tend to expand slightly. They get colder, they tend to contract slightly, and that can be said for solutions. So going between 5 degrees Celsius and 95 degrees Celsius, it's still the same 2 moles of solute in there, but look, the volume of the solution would have changed. So no longer would we have a 2 molar solution, 2 moles per 1 liter. Now we would have 2 moles of solute. If we look over here, still 2 moles of solute, but that's greater than 1 liter. So 2 moles of solute divided by greater than 1 liter, that's going to be less than 2 molar. So that can be a problem. It is measurable. It doesn't fluctuate much, but it can be a problem. The other way in which solution volume can change is if we go through a change of physical state, meaning liquid to solid or solid to liquid during the time the experiment is being carried out. So for instance, liquid water, when it freezes to solid water or ice, it expands somewhat, such that the density of liquid water is exactly 1 gram per cubic centimeter, but the density of ice is 0.93 grams per cubic centimeter. It's the reason that ice cubes will always float on the top of a drink and never sink to the bottom. So that can be an issue too. If the experiment we're carrying out, which requires concentration, goes through a physical change, that's going to be an issue. That's going to be an issue because the concentration, if we used molarity, would essentially change. Again, perhaps not much, but it can be measurable. So let's take a look at this concept of molality that we talked about before as a different, more accurate method of determining solute concentration. So now, while solution volume can fluctuate under the 2 conditions that we just talked about, changes in temperature or changes in state, volume changes, but mass will not change. The mass of the solution or the mass of the solvent, that's 1 kilogram of solvent at 5 degrees is 1 kilogram of solvent at 95 degrees. So this new way of looking at concentration, that of molality, is still moles of solute in the numerator, but we change the denominator from liters of solution to kilograms of solvent. Kilograms of solvent. So that the units of measure for molality are moles per kilogram. Moles per kilogram. Now, whereas we represented moles per liter in molarity with a capital M with a line under it, the molality is a lowercase m with a line under it. Whereas if we talked about it phonetically, I have a 1 molar solution of NaCl, well, we could say I have a 1 molal solution of NaCl if we're talking about molality. So it's similar, but there are some interesting differences. Really, the key here is if we're calculating molality, this is what we're aiming for: moles of solute per 1 kilogram of solvent. Let's look at an example. All right, for example, calculate the molality of a solution containing 17.2 grams of ethylene glycol. Notice we give the chemical formula C2H6O2 dissolved in 0.5 kilograms of water. Now, so be careful first, because it's very easy to look at the word molality and think molarity. It's very easy to do that, so just be careful because they're calculated in 2 different fashions. So we want molality. Molality is moles of solute per 1 kilogram of solvent. Are we given moles of solute? No, we're given grams of our solute, and we have to convert that to moles. Thankfully, we have our chemical formula given of our solute, so we can easily calculate the molar mass of it, as we've done before, 62.08 grams per mole, and then we convert from that gram mass using that molar mass as a per expression to give the number of moles of our solute, C2H6O2, at 0.277 moles. Now, molality is number of moles per 1 kilogram of solvent. This that we have here is the number of moles per 0.5 kilograms of our solvent. The way to make that into an actual molal per 1 kilogram of solvent is take that number of moles that we have and divide it by the actual mass, 0.5 kilograms of our solvent, and that would give us 0.554 moles per 1 kilogram, or 0.554 molal. So now we'll look at a practical way of applying molality. When would we have to use molality? There are a number of times we would have to use molality, but one of the main ones that we talked about was during an experiment during which we go from one physical state to another, liquid to solid or solid to liquid. And to introduce this particular example, we have to look at something known as colligative properties. There's solution properties are called colligative properties if they're determined only by the concentration of a particular solute in it. An example of this would be freezing point depression. Freezing point depression is ultimately, if we have a pure solvent like water, for instance, water freezes at 0 degrees Celsius, turns to solid. With the introduction of any dissolved particles within that water or any solvent, we can think of those dissolved particles as an impurity, perhaps, but the freezing point always becomes somewhat lowered. So if I dissolve something into water, and test its freezing point, is always going to be below 0 degrees Celsius. Now, the thing with freezing point depression, it is a colligative property because the higher the concentration of the impurity or whatever is dissolved in that solvent, in this case water, the greater the freezing point depression, the greater depression we get, effect that we get on our, if we were to freeze that now solution. We have an equation for that. It's called the freezing point depression equation, and it's given here as delta T sub F. Delta means change, sub F means temperature of freezing point. So we have the change in our freezing point in degrees Celsius equals a freezing point constant, and that's separate, that's different for each solvent. So for instance, for water, it is this value right here. For others, it's other solvents, it's different values, times the molality of that impurity. Whatever solute we have dissolved in there, that is the molality. So we are able to calculate the freezing point depression of a particular solution if we know what solvent it is. So we can know the initial freezing point. We can calculate how much that freezing point is depressed based upon the concentration of our solute in there. Now notice we use molality here because molality does not fluctuate with changes in state. Remember that, right? By definition, observing a freezing point depression, we have to go through changes of state. We have to go from liquid to solid. So that's why we're using molality in this case. So here's an example of a freezing point depression calculation. Calculate the freezing point of a solution containing 12 grams of urea. Here there is our, again, our chemical formula, dissolved in 0.25 kilograms of water. Well, we see freezing point, anything that's a freezing point depression, what's the freezing point, etc., all that. We know this is a freezing point depression calculation. So that's so we'll know how we're going to go about this. So freezing point depression, to know that amount that the freezing point is depressed on that from the original freezing point of the pure solvent, we have to know the molality. That's where we're doing the most work here, the heaviest lifting, if you will. And molality is moles of solute per 1 kilogram of solvent. Again, we're not given moles of urea, our solute. We're given grams of urea. So our first task is converting the grams of urea to moles of urea by first figuring out the number of, or the molar mass of urea, and again, I put that out there just for you, 60.06 grams per mole, and taking that 60.6 grams per mole and using it as a per expression to convert to moles of urea. So this is great. Now we have our moles of urea, and the molality is moles of solute per 1 kilogram of solvent. Well, This is zero. We have 0.2 moles of urea per 0.25 kilograms of solvent right now. How do we make it per 1 kilogram of solvent? Well, we take those number of moles of urea and divide it by whatever mass we had, 0.25 kilograms of water, and that gives us 0.800 moles per kilogram. That's or 0.800 molal. So that's what we have. We have half of our equation that we need. Now we plug the number into the equation from the previous page. This is what we're looking for. This is our delta T sub F right there. That is our chain, that is our freezing point depression. Multiplied first by the freezing point constant, it is indeed water. So you'd be provided a listing for something like that. So we have our freezing point constant times the molality. And there it is, times the 0.800. It's that simple. And that will give us our freezing point depression, and it would be tempting to say that we're done right now. What it said that we've calculated the freezing point depression, but if we look up at the top, it's not asking for freezing point depression, it's asking for the freezing point. So the freezing point itself, we have to take the actual freezing point of, in this case, water, and subtract that number from it to give us our final answer, our freezing point depression. This is what the new freezing point of that water is.